Hi guys, welcome to Maths with me, Miss Rosie, your teacher for today. So today we're gonna discuss about inertia and equilibrium, Newton's first law of motion. In 1687, Isaac Newton published one of the greatest scientific works of all time. His Philosophia Naturalis Principia Mathematica, the Latin title translates as the Mathematical Principles of Natural Philosophy. In the Principia, Newton stated three laws of motion that form the basis of classical mechanics. These laws describe how one or more forces acting on one object affect its motion and how the forces that interacting object exert on one another are related. Together with his law of universal gravitation, Newton's law of motion showed for the first time that the motion of the heavenly bodies, the sun, the planets, and their satellites, and the motion of earthly bodies can be understood using the same physical principles. To pre-Newtonian thinkers, it seems that three must be two different sets of physical laws. One set to describe the motion of the heavenly bodies, thought to be perfect and enduring, and the another to describe the motion of earthly bodies that always come to rest. Newton's first law says that an object acted on by zero net force moves in a straight line with constant speed, or if it is at rest, remains at rest. This concise statement of Newton's first law includes both the case of an object at rest and a moving object. Certainly, it makes sense that an object at rest remains at rest unless some force acts on it to make it start or move. On the other hand, it may not be obvious that an object can continue to move without forces acting to keep it moving. In our experience, most moving objects come to rest because of forces that oppose motion, such as friction and air resistance. A hockey puck can slide the entire length of a rink with very little change in speed and direction because the ice is slippery. If we could remove all the resistive forces, including the friction and air resistance, the puck would slide without changing its speed or direction at all. No force is required to keep an object in motion if there are no forces opposing its motion. When a hockey player strikes the puck with the stick, the brief contact force exerted on the puck by the stick changes the puck's velocity. But once the puck loses contact with the stick, it continues to slide along the ice even though the stick no longer exerts a force. Newton's first law is also called the law of inertia. In physics, inertia means resistance to change in velocity. It does not mean resistance to the continuation of the motion. Newton based the law of inertia on the ideas of some of his predecessors, including Galileo Galilei and Rene Descartes. In a series of clever experiments in which he rolled a ball up inclined of different angles, Galileo postulated that if he could eliminate all the resistive forces, a ball rolling on a horizontal surface would never stop. Galileo made a brilliant conceptual leap from the real world with friction to an imagined ideal world free of friction. The law of inertia contradicts the view of the Greek philosopher Aristotle, Almost 200 years before Galileo, Aristotle had formulated his view that the natural state of an object is to be at rest, and for an object to remain in motion, a force would have to act on it continuously. Galileo conjectured that in the absence of friction and other resistive forces, an object in motion will continue to move even though no force is pushing or pulling it. However, Galileo thought that the sustained motion of an object would be in a great circle around the Earth. Shortly after Galileo's death, Descartes argued that the motion of an object free of any forces should be along a straight line rather than a circle. Newton acknowledged his debt to Galileo, Descartes, and others when he wrote, "If I have seen farther, it is because I was standing on the shoulders of the giants." When the net force acting on an object is zero, the object is said to be in translational equilibrium. Equilibrium conveys the idea that the forces are in balance. There is as much force upward as there is downward, as much to the right as to the left, and so forth. Translation refers to the motion without rotation. Any object moving with a constant velocity, whether at rest or moving in a straight line at a constant speed, is translational equilibrium. A vector can only have zero magnitude if all of its components are zero. In an equilibrium problem, choose x and y axes so the fewer number of force vectors have both x and y components. It is always good practice to make a conscious choice of axes and then to draw them in the FBDs and any other sketches that you make in solving the problem. Using Newton's first law, you can understand how a spring scale can be used to measure weight. If a melon remains at rest in the pan of the scale, the net force on the melon must be zero. There are only two forces acting on the melon. Gravity pulls down and the scales pulls up. Then, these two forces must be equal in magnitude and opposite in direction. The scale measures the magnitude of the force it exerts on the melon, which is equal to the weight of the melon.